Hello everyone, I'm going to introduce Julia programming and show you what advantages Julia has. I make plots and calculation in Matrix. Julia is a high-level, high-performance dynamic language for numerical computing. I ran the escape time algorithm and it spent 4 seconds in Julia and about 12 million in R. Let's get into Julia program. Let's do calculation in matrix. Matrix A equal 1, 2, and 3, 4. Matrix B equals 1, 1, 1, 1. You can calculate matrix A plus matrix B, and also can calculate matrix A times matrix B. Ten times our matrix A and transpose matrix A and inverse matrix A. Next, we are going to using the gate flight function to draw a plot. So here's the plot for the exponential distribution with lambda equal 1. Next, we are going to do the for loop using distributions. We set x equals 0 and for I equal 1 to 10,000 and x equal x plus random uniform 1 to 2. Let's do times x is equal to 1.5 times e to the power to the 4th power, and that's for all the introduction to Julia.
My name is Shunren, and I'm going to demonstrate how to write functions in Julia by showing two very simple examples. The first example I'm going to show is the Fibonacci sequence. We know that the Fibonacci sequence is a sequence that each number in the sequence is determined by the sum of the previous two numbers, except for the first two initial values, 0 and 1. So in this Fib Julia n function, if n equal to 0, the Fib Julia n will equal to 0, and if n equal to 1, the Fib Julia 1 will be equal to 1. So we can use this function to calculate Fib Julia 40. The second example I'm going to show is the Gibbs function. What this function did is that we tried to generate n numbers from a normal distribution and generate n numbers from a gamma distribution. So we can calculate the mean of the numbers we generated from normal and the mean of numbers we generated from the gamma. The first thing we did is that we created a n by 2 matrix filled up with 0 and replaced the first row with a starting vector. And for row to column 1, we replaced the 0 with a number we generated from the normal distribution, and we replace the row to column 2 with a number we generated from the gamma function, and so on until the nth row. And then we can calculate the mean for column 1 and the mean for column 2. So we can use this function to do this big calculation.
So my name is Eric, and I will be showing you how to run the Gibbs sampler in Julia. So the function itself is very similar to R in terms of it takes the same variables. The function takes the same variables, same initial conditions, except we have this X array, which we fill with zeros, and we will fill it up with our mu, tau, and sigmas as we run the for loops. So we set our initial conditions here, and then we have these post shape, rate, W, temp tau, and temp mu. These are all from the conditional densities of the posterior that we derived in class. So this first chunk is just burn-in. Basically, we throw away these loops in order to be more precise with our iterations, so we're not wasting iterations. And then for our iterations, where we have and then just one here, so essentially this J part is just non-existent. So we run the exact same code as up here. We sampled the tau and the mu from gamma normal distributions with these given quantities. Again, I said we derived in class. And then those values are stored in this array, this X array that we defined earlier. And then this just takes the mean of those columns and rounds it. And so we can just run the Gibbs norm here, I call it, function, and I just set these variables just to run a test run, and then we get these estimators for mu, tau, and sigma. And so that's basically it.